All right, let's get started. So I'm excited to talk to you guys today about decoding, detecting, and diagnosing your LLMs and troubleshooting user behavior changes and performance drift. So today's workshop is all about understanding when we see change in our data or our models or systems, what's going wrong and how do we distinguish between different causes of those issues? How do we detect? How do we decode the kind of data, the massive data that we see? How do we detect the issue that's going on, that an issue is going on? And then how do we diagnose exactly what issue that may be? Okay, so here's my agenda for today's workshop. It's 1 hour. So I'll do a quick introduction to both myself and Y Labs. Then we'll talk about data distribution. So jumping into some of the statistics, thinking about what data looks like both for the structured case and the unstructured case. And then we'll talk about detecting change in your data. And so this can be due to a number of causes: user behavior, system behavior, underlying relationships, data quality are the four that I will talk about. And we'll talk about them in the context of a specific set of metrics, especially when we think about text. Okay, but before we do introductions to myself and Y Labs, I do want to ask for introductions for all of you who are joining, either on LinkedIn or on YouTube. So feel free to write in the comments your name, where you're coming from, both the physical location, but also kind of your experience level related to data and related to machine learning and monitoring machine learning and LLMs in particular. All right, I'll give people time to do that as I go through and introduce myself. So I am Bernice Herman. I have been, had a mohawk back then. I should change my picture now. But I have been a data scientist for 12 years. And I work both in academia at the University of Washington, eScience Institute, and in industry here at Y Labs. So it's worth noting on one of the earlier slides that while I am in both of these positions, I'm coming from my perspective at Y Labs, so not the university side of things. And this is just for legal reasons. Prior to working at either of these two places, I worked at Amazon as a software development engineer. And then for fun, just to include a hobby, one thing I like to do is develop games, so video and tabletop games, as well as weightlifting. Okay, so hopefully you guys are still introducing yourselves in the chat or getting ready to do so. But as you do that, I'm going to introduce Y Labs and what we do here. So at Y Labs, we're really focused on helping to detect, prevent, and mitigate risk in your AI applications. And so this often is really difficult to do at a production scale. There's many tools out there to help you kind of experiment with AI and machine learning. We may be familiar with many of those tools. And while you can use Y Labs tools to experiment, we're really focused on kind of the production setting and all of the many challenges that come in the production setting. So the picture you see here is kind of a high-level idea of what you may see. So you have in a production environment, and there's so many different sources of data that are available to us and coming into our system and going out of our system. So you may have live inference data. This might be something like streaming data, where in real time, you're getting data from your customers and you're passing them into some application of yours. So the perspective I'm taking for this workshop is sort of like you are the creator of some AI application or system. It's often wrapped around a model. So a model is just one piece of a larger system with guardrails and code and different interactions that you have with the customer. But so if you are creating some larger system, you may get live inference, so situations where you want to call the model and get the response directly right away. in a one-by-one basis. You may do batch inference. So this may be, for example, if I'm running my machine learning model every day in the mornings to calculate the new email that I push out or new changes to the web page, as opposed to kind of doing this instantly in real time. You have things that we mentioned like offline training and testing. So something more related to our experimental setup, where we will, maybe run a large batch of data because we want to run on our training data set, retrain our model, or we might want to run on testing data sets or things like this, experimenting. And there's lots of other sources of data, so feature stores and so on and so forth. So we take a data-centric approach. So thinking about all of these different systems that your application is comprised of as data, as inputs and outputs, most simply. So when you do that, what you can do is collect snapshots of that data or metadata around that data that we consider AI telemetry. So we can use this data as telemetry for downstream systems to understand what's happening inside of it. And so you'll see that little orange square here. And then that gets passed into our AI observability platform where you can now combine this and look at this over time, monitor, give alerts, find anomalies, visualize that data. And then you have workflows that go off of that to interact with your coworkers in communicating to data scientists when this model needs to be retrained, or to the engineers or to business stakeholders as well. Okay, so I'm going to largely talk about 3 parts of why labs in the context of this workshop. So the first is why logs. This is an open source library for data profiling and generating that telemetry. So we're really focused on kind of privacy first perspective. We don't need to store the raw data or pass around the raw data from your applications. In many applications, it's not feasible at all. But what we can do is collect metadata or statistics about your data. And we use data sketches to do that in an efficient way. And I'll mention that briefly later, but this won't be the focus of today's workshop. So that's all open source and free to use in YLogs. So next, so we'll talk a lot today about where structured data, we may just use statistics kind of as we expect. When we move to text and other unstructured data, we now need to collect different metrics on top of that data. So LangKit is our opportunity to collect those metrics. So we have a toolkit of many, many different types of metrics that you would need for text to better understand that text and convert them into something that is understandable to us and able to kind of analyze for trends and understand. And finally, the YLabs AI Observatory. So this is where we're going to now not just look at a single batch of data or look at data at one snapshot, but look at lots of data over time and start to find trends, start to create actionable workflows to determine what you're going to do with this data, understand when there is a pattern that is concerning or an issue that we can go and act on, or just understand historically what's happening in our data. Okay, so those are the 3 that I'm going to focus on today. And I just want to give a little context now about my perspective within those 3. So I, as a data scientist, focus pretty heavily on statistics and machine learning. So on the YLog side of things, thinking a lot about how do we compress the data? What sort of algorithms do we use? Because we're gathering statistics about our data. So lots of statistics there. In LangKit, this is about metric selection. So what information about text do we need to capture? And then finally, on the on the platform side, looking for monitoring and anomaly detection algorithms. Okay, so now let's get to the statistics sides of things. And so we're going to start with a little refresher on data distributions and some thinking about how this differs for structured and non-structured data. So first, structured data. And what do I mean by that? Well, Here, we're just going to focus on tabular data, which is the most common way that this term's used. And so tabular data looks something like this. I'm pretty sure all of you have seen something like this, if not this specific data set. If you can read this, if this is large enough for you and you can tell what data set this is from the column names, feel free to type it into the chat as well. But what we see here are multiple rows and multiple columns of data, something pretty standard that we're used to seeing. And the data is numerical in some of these columns and categorical or text data in others. So the difference between categorical and text data is that categorical data is often, the text is just representing one of a set of different values that we consider valid. So in this case, we have a number of species of flower that we can accept here. And what we see in blue are input features. So in the blue on the left, these are features that we're using inside of our machine learning model. And then the things that we see on the right in orange are outputs from our model. So this can include things like the prediction itself. So you might notice that this is a classification model, but then also confidence for that prediction. Okay, so once we have this sort of numerical data or categorical data, there's a lot of useful statistics that we can calculate on each individual column. So some traditional statistical properties that we're interested in, things like location. So what's the mean, what's the median of our data? Where's that center? And where are the edges? So spread, what's the range? What's the variance of our data? Shape. So can we fit some sort of parametric distribution to this data? Is it uniform? Is it Gaussian? Is it some other sort of distribution? And maybe it's not. Often in production settings, we won't have a particular shape. Unless you have a certain volume of data, then you may see Gaussian for sure. But there are many other properties that we're often concerned about when we're thinking about data science kind of in the real world, that aren't these traditional statistics, but are things like data type information. Are they integers? Are they fractions? Are they strings, right? This is something that people who've worked with databases are really familiar with. And as data scientists, we're quite familiar with as well. Missing values and unique values. So how many nans do we have, or missing values or unknown values do we have in our data? What's the proportion? What's the count? Same for unique values and many, many other properties. So we can capture this data and we can start to collect these different metrics and this information. But the question is how do we do this at scale? So sometimes I go through kind of different alternatives for working at scale, but I'm going to jump straight to the approach that we use, which is sketch-based profiling. So we want to, instead of keeping all of the raw data or even a subset of that raw data, what you lose in that case is often some of the tail data. So some data, if you have very rare events and you only store 1% of the information, maybe you won't capture the information you want. But what you can do is start to capture using statistics, so using data sketches, to capture kind of a sample of the most important tails of the data that's also representative of the whole distribution. So this is a really interesting algorithmic approach that is used in research, often in the database world and in theoretical computer science. But it provides us with some really nice things when we're thinking just about storing our production data. So one is, by capturing specific metrics, we have fast access to those metrics. So if you imagine, if I have, let's say, billions of rows of data per day, we don't want to calculate, certainly we don't want to calculate things like the median on that data whenever we want to do analysis or whenever we want to understand what was going on. What we would like instead is to capture those metrics in time. So we're able to do that with profiling techniques. And then we want high flexibility. So one problem with other techniques of profiling is you might capture a median for our data, but it might turn out that we had another machine and we want to combine that information together. Or now I want to know the median across the entire last week, not just yesterday. And it's really difficult. There are many metrics that are very brittle. Sketches give us some flexibility, which is really nice. They're mergeable. They're built, again, on this academic research. And they do have a couple of cons that are common to profiling things. So you do have to kind of have some idea of what metrics you're going to capture, although you can add more later. And then there's the underlying complexity of kind of using this research. Okay, so that was some technical stuff on how Y-logs, the kind of first step for this, works, and how we think about profiling and storing data for structured data. So we haven't quite gotten to diagnosing. We'll get to that later. But let's go ahead and jump into a short demo. So if you go to this link here, bit.ly/dsd-langkit-v2, this is the second version of this notebook here, we are going to look at this. Oh, don't want to be signed out. That will be bad. Let's see here. Oh, sorry, 1 second. Okay, so let's see. Share screen. All right, apologies. Google decided to sign me out right then. So let's get started with our notebook here. I'm going to disconnect and start over so that we're all on the same page. But we're going to go through this first section just to understand how profiling structured data works. Okay, so the first thing we're going to do is we're going to do some imports for the entire workshop here. So we'll pip install LangKit and LangChain. So LangKit actually imports Y-logs. You'll see what you might have seen there. So we won't need to pip install Y-logs individually because LangKit actually depends on Y-logs. But we will install both of these. And the LangChain is just for later, the very last demonstration if we get to it, using OpenAI. All right, so we've installed. Let's go ahead and import Y-logs to start. And after this is imported, we're going to do an init. So this is just to determine what sort of settings that we have here to create a session. We're going to do this session using the anonymous sessions, although there are some features that are really helpful with an API key. So if you have an API key, feel free to type in one and pass that in, but we'll just do anonymous for now. Okay, so let's just import pandas here. And I want to import the data set that we have here. And actually, I'm not going to use this data set here because we have a copy of it now in LangKit. So I can just use that one here from LangKit Y-log samples, load chats. It's a little bit different, but that's okay. And what we get is a data frame, pandas data frame, with 2 columns, one with prompts and one with responses from an LLM. So these particular prompts and responses are from GPT 3.5 Turbo a couple of months ago. And what this is kind of representing is a number of calls to an OpenAI or any LLM that you may have as a part of your application. So we won't maybe go into detail about what that application is. We'll give a different example later today. But this is just an example that hopefully looks to be in a familiar form to you. Okay, so let's start thinking first about how Y-logs work. So as I mentioned, we talked about structured data, which is kind of numbers and categorical data mostly, although you can use text in some cases. And so we want to think about what is Y-logs doing, kind of what is it replacing, first of all. So one problem that you might run into, maybe not with such a small data set as we have here, but in a production environment, we have a lot of data and we're thinking about how this scales. And so we might do a couple of things to store some information so that we can go back in the past and analyze our data or find trends in our data without storing or having to parse every single bit of data that goes in and out of our model. So to do so, one thing that people do is they may store a random sample of their data. So if I wanted to store 5% of my data, I could do something in pandas, for example, like taking my data frame and calling the sample method on it. So if I look for 5% of my data, that's going to be a pretty small amount just because we have a small amount of data for our example, but really helpful when we have a lot of data in production. So that's one approach. The other approach that I talked about was data profiling. So I sort of split data profiling into 2 sorts of types. One is simple data profiling, capturing a number of just individual numbers about our profile or descriptions. So if I use the example from pandas, again, we can use our data frame.describe, and this will profile our data. So what we see here is that our prompt column has 50 values, but only 47 unique values in it. And then gives us a mode, so which value is seen most and frequency of that mode. So what you might conclude from this, and what hopefully you do conclude from this, is that our data set has 3 copies of the same value, and that value is this, and both for prompt and response. Okay, but we have, again, some problems. So if we wanted to take the median, or we wanted to do a number of metrics that don't quite add up together. So for example, if I have a mode, this top line here, for some data, and then I have a different mode for tomorrow's data, I may not know what the mode is across the whole week's data. But if we use something more complex for profiling, we can start to capture some of these information. So let's just use Y-logs. So it's very, very simple to do. So we've imported Y-logs as Y. I'll just scroll up here. So we've imported Y-logs as Y. So when we come down here, we can just do y.log and then pass in our data frame, chats. And there's many different ways we can pass in data. So we can pass it in as a dictionary instead, but we'll just stick with our data frame for now. And what we see is that we've aggregated those 50 rows into a data profile. If I click on this button here, this is going to open up the platform, the YLabs platform, and give us an opportunity to sign up for a free account. So as I mentioned, now we'll just go with the anonymous session, but please do click on this and then take the tour. There's many, many more features, such as creating a monitor, such as looking at historical data that you can't actually do without signing up for an account. And it's totally free. Okay, so now we see our profile of data here. We see prompts, we see responses, We see a date, which is just today's date. And we can look and see some details here. Sorry, my screen is super zoomed in. And so you'll see here that we have a distribution, but we actually do see some data, and that's because by default, I have it set to pass in just a number of samples. So this doesn't have every data point. This has, I think, about 30 data points. But if we want, we can not pass this in at all because we have a lot of statistical information. And that statistical information is actually what we do our monitoring on for the most part. Okay, so this is really great. This tells us lots of things, count, null, fraction, that sort of stuff. But it may not be that helpful for text, right? We don't really have a lot of insight about the text itself. And so let's go ahead and learn a little bit more about how to fix that. Okay, so let's move to unstructured data. So unstructured data, so here's one challenge that we might have when we have text. What we don't want just the raw text. What we want is some information that helps us to understand what's happening in the text. So one challenge might be that I'm trying to understand how many references this text has, or maybe like how news-like is it? How, I don't know, academic is it? Let's see, some sort of kind of semantic understanding of the text, and some sort of kind of specific meaning of a metric that we capture on that text. So one way we might do that is capture entities. So count how many times we find a kind of formal entity like a person or an organization or a date in our text. And this is something that statistics generally isn't equipped to do, but we can use natural language processing to come up with metrics that we can then do statistics on top of. Another text challenge is something like hallucinations. So this, if you haven't, if you're not familiar with hallucinations, this is a really interesting example of one where we've passed into an LLM a question to summarize this article and then passed in a fake URL. So this actually doesn't go to a real web page, and yet the LLM responds with an actual description based solely on just the URL passed in, right? So it says content filters inside of the URL. So a whole made up paragraph on this article in content filters. And coming up with metrics can be really difficult. The exercise I like to do is with images, just because it's a little bit easier sometimes and a little more fun. But think about this example here where we have two sets of images. They happen to be the results of a GAN in 2014 and the results of a different GAN in 2017. So vast change in quality of these two images. And yet this task that we're kind of faced with whenever we want to use unstructured data and do analysis of unstructured data is coming up with metrics that make sense to us, that are meaningful. And so one thing you can try to do is come up with metrics that describe the quality of these two images in a way that would distinguish between these two sets of images. So we won't have time to actually do it, but feel free to write your thoughts in the chat. But some metrics that you might come up with are, first, people say things like number of eyes, and that is a relevant one, right? So we see in the lower quality images, it's not quite that every person has two eyes in the pictures, but this is something that isn't really easy to describe to an algorithm, right? Like this is still very kind of general and something that isn't precise enough to actually capture metrics about. So the sorts of metrics that you might capture are things like, what does the color gradient look like from left to right in each image? And is that gradient kind of strong, or is it sloping softly? That sort of things. You might do other things like comparing to a composite face. So if you take many pictures of faces on top of each other, you'll actually often see some sort of structure. And if we can compare each face to that composite face picture, maybe we'll understand some sense of quality. Now, you may also use a model itself to describe data about the output of a model. So if we used some sort of image detection algorithm that tells us things like number of eyes, or tells us things like predicts gender, or predicts age, or something like this, even if you don't use the gender or age, taking that information, or taking the consistency of that information or metrics about that model can be really helpful as metrics for us. Okay, so that's for images, but these are some examples that we actually use in LangKit for text. So things like text quality as it relates to complexity and grade scores and readability scores, things like similarity between the prompt and the response as some measure of relevance, things like similarity from the prompt or the response to user-defined themes. So you may say something like toxic text, or text specific to your use case. We want to know that the response to the LLM is relevant to that text. There are many, many, many security and privacy metrics. The focus of today isn't really on those, but just to name a couple here on the slide. And then finally, sentiment and toxicity. So things like how toxic is the text? Does it include curse words? Does it include kind of bad language? As well as what's the general positivity or negativity of the text. Okay, and so having complex metrics like this, even when they cover a variety of issues and maybe not specifically the issue that you're looking at, when in combination, tell us a lot about the data for unstructured data, regardless of kind of what data type comes in. So if we use, for example, LangKit on text, we can get numbers like sentiment, number of entities, jailbreak, the probability of this text being a jailbreak by virtue of its similarity to a set of jailbreaks, refusals, toxicity, that sort of thing. And once we have this structure here, we know what to do with it because we've already seen this with ylogs. We can pass it into ylogs. And so then we can calculate all of these sorts of univariate metrics again: location, spread, shape, missing values, etc. Okay, so now let's go back to the demo, but this time let's look at our text data using LangKit so that we can get maybe better metrics, more helpful metrics for us. Okay. So now I'm going to get to this getting started with LangKit section. I will minimize this. Okay. And the first thing we're going to do is import one of the modules in LangKit. So the one we'll do today is light metrics. And the reason for this is that there are many different metrics that we have, but we have the ones that we kind of want to talk about today, which are really focused on kind of text quality metrics, things like this. So once we've imported light metrics, the only thing we need to do is initialize this module. And when you initialize a module, we want to pass it into a schema, and we'll use that in the next line here. So let's just say schema equals light metrics. When we use LLM metrics, it goes pretty slowly because there's a number of machine learning models underneath. Like I mentioned, light metrics is a little faster, so that ran very quickly. And now we're going to do the same call that we did earlier, y.log, but we're going to pass in a specific schema. So we save this as schema. We'll pass this in, and then we'll also give it a name so that we can distinguish it from the data that we saw earlier. So when I run this line, we're going to profile these new 50 rows of data. And when I click on this link here, we'll now see a different data come up. So, let's see here. So the first data that we pass in, we didn't give a name. So the platform kind of treats this as a production data. But when we give it a name, we're kind of treating it as a different separate reference profile. And if we hadn't done that, it would get all merged together. That's not quite what we want to see today. Although in your normal applications, that's kind of the more common case. Okay, so what do we see here? We see first our prompt column that we saw before, but we see now many more columns. So things like prompt.aggregate reading level. And if we look at this, we see some distribution of reading levels. And so we can see, for example, that the mean reading level is 7.58 and has a min and range and that sort of stuff. Same for a number of things: character count, difficult words, other reading level sort of things, so reading ease, about the complexity. Things like has patterns, so this is actually about security. So we may see some data leakage in our data, which we have. So we see 2 examples of email addresses and 2 examples of social security numbers in our set of prompts, our 50 prompts. We also see different text metrics, so letter count, lexicon count, monosyllabic words, things that have multiple syllables, number of sentences, that sort of stuff. All of this is very helpful in translating kind of what we had initially of just text to metrics that are actually, meaningful, can help us understand things. So we might see, for example, if we compared yesterday's to today, maybe we see an increase in difficult words or the distribution of difficult words, right? So this might tell us something about user behavior for today. We might see, for example, something like more social security numbers or more data leakage in our prompts. This might tell us that our application that we've built that's supposed to filter these things out hasn't done so as well as we would hope, and that sort of thing. So we have similar just for prompt. We also have the same for response, all of the same metrics. And we see, for example, in the responses, in addition to social security number and phone number, we have mailing address and credit card numbers. So this is even more interesting because this is saying even when we didn't have examples of credit card numbers passed in, we see them passed out. And that could be the model kind of leaking information. That could be, it depends on the question, that sort of thing. And we'll learn to kind of diagnose these sorts of things in a bit. Okay, so let's go back to our demo here. Oops. And let's look at some specific metrics. So one thing that we've done right now is we've just logged and sent them all the way over, kind of packaged our data into a data profile, but we didn't really inspect what was happening. So we can do that by taking our schema and running a different call on this, apply UDFs. And I'm wondering, did I import this in order? Oh, I did. Great. Oh, right. So we have our schema, apply UDFs, and we're going to apply that to chats. And this is going to give us a augmented profile or augmented data frame of our chats. So what we can do is look at this. We'll skip the columns for now. Let's just look at the chats themselves. So now, instead of just the profile, this is just LangKit. What we're seeing is kind of an augmented version. So all of these calculations on the raw text. So remember, when we pass in a profile, that's largely metadata. So this kind of detailed text is not being passed into the platform in any way. It's not leaving your machine. But we do have it available here since we're running LangKit locally on our own machine before we pass on the compressed data. We do have it locally to inspect. So we can see for each row, the values for all of these, not just kind of the statistical distribution, although that distribution is often all you need. Okay. So we talked about this, but there are things related to sentiment, toxicity, and vocabulary metrics such as number of syllables and things like that. Okay, one thing this actually doesn't have, and that is sentiment. So I apologize, I misspoke there. So in light metrics, by default, it doesn't contain sentiment. And I want to add sentiment to this. So I want to show you how you might add more metrics. So first, we're just going to add a module of metrics that already exists in LangKit. So the way that you do this is we import our new module from LangKit. So from LangKit, import sentiment. This is very similar to what we did before when we said from LangKit, import light metrics. And now we just need to capture a new schema. I apologize, I named this two different things here. So from ylogs.experimental.core UDF schema, we have a method here called UDF schema. So we're just going to import that and run it, and then pass this into our same schema variable we had. And so now we have a schema object that has all of the information about the original light metrics that we had in our schema, as well as registering our new import, our sentiment. So now, if we run the same function here, schema.apply UDFs, or if we ran y.log, we would see these new metrics. So let's look at this, augmented chats. And so we see all of this text, but we should also see our sentiment. That is captured from, the default model is from NLTK. So we should see, yes, both negative numbers and positive numbers, depending on the text that you pass in, of course. So that's good to see. Awesome. So that's how you import new modules. I will leave it as an exercise. You guys can go through and learn how to create a completely custom user-defined function that does a very similar thing. It adds a new column with the information that you want. And the basics, what you do is you import this decorator and apply it to any function that can augment your data. Okay, but let's jump back into the presentation and think about user behavior and why these tools might be helpful. Okay, and to do so, we're going to start with dataset drift. So we talked about a number of different statistics that we might have available to us: location, spread, shape, missing values, data types, that sort of thing. But there's one thing that we haven't really talked about, and that's comparing more than one column. So to do so, we often think of this in terms of drift. So how might you detect data drift? One is just to compare distributions. So I might look at a histogram of yesterday's data, look at a histogram of today's data, and say, hey, these aren't very aligned. These don't look like the same distribution. Something has drifted. This is a common way of doing this, but obviously we want to step up a little bit. So another way you might do this is some sort of rule-based verification. Maybe I say, well, if the median for this value has increased by 20%, I'm going to consider this drift. And this is a common way to do this, and often a way that even in production, data scientists do this. But it, of course, can be very finicky. It takes a lot of work to create those rules and maintain those rules. And it doesn't really capture kind of all of the things that we have learned to capture using statistics. So things like, what are the counts? How many different values are there? If there were 3 values yesterday and 300 today, that's worth noting, even if they happen to have the same mean, right? And so we have available to us statistical tests and different distribution metrics that are standard for this task. So some examples of comparing two univariate distributions. And so when I say univariate distribution, what I mean is that even if we have a data set with multiple columns, we're often comparing column to column. So things like Hellinger distance, things like KL divergence or distance, things like the KS test. So this is a statistical test. Chi-squared test when we have categorical data. So now let's think about what happens. How do we move beyond maybe detection? Because that's what using these sorts of tests to say, okay, there has been drift is. So often these tests will tell us something like, yes, there has been drift, there has been some change. And that's really helpful because at least if we can find out, well, today at 5 o'clock, there was some change, we can go back and say, okay, well, we've made a code change or something may have happened, or in April 2020 this change happened. We can look around and say, okay, well, COVID is happening, this may have caused the change. But it's even better if we can start to figure out where that change might be happening. So one way we can do that is actually looking at very simple breakdowns of these distributions. So you're probably familiar with Bayes' formula right here. But this can help us define, for example, in one formulation, concept drift. So we'll talk about this, and then label shift, we'll talk about this. And then in another formulation, we can find other ones. Okay, so now let's set up a scenario so that we can talk more deeply about finding specific issues in our data. So here's the scenario we'll use for the rest of the presentation. Online, we're going to be pretending that we're an online international clothing retailer that serves adults. And we lead the machine learning and data science team that predicts the most likely clothing type for each customer. We're going to use some variables here. So X is going to represent the inputs to our model. And in our case, it's going to be things like customer information. So demographics, maybe the age, maybe the gender, home location, like what state and city they live in, income if we have it, that sort of thing, how much they've spent on the website over time, and then also site usage information. So this might be how often do they come to our site, how many web pages have they clicked, how long do they spend on average on different clothing item web pages. And for our Y, they're just going to be the outputs of the model. So in our case, this is going to be our model's prediction of the preferred clothing type of this customer. And we're going to say that at this time, it only predicts like a single best, most preferred type. Okay, so now let's go through 3 scenarios for detecting change, and 3 different causes, actually 4, I apologize, 4 different causes for this change. 3 of them are easier than the last one. So the first is user behavior. So let's actually start here. So our scenario, adding new customers. So let's say that we opened up our business, our retail business, to a new customer segment. Originally, we only served adults. Now we serve children and teens. So now we want to ask ourselves, looking at that earlier formula, what could have changed? What could this mean? So our distribution of X, remember X is our variable for all of the inputs to our model, all of the customer information. So our overall distribution of X has changed. While we used to see some subset of customers that are related to adults, we've now added kind of new data points that are going to be in a different spot in space, right? Because we do collect things that would relate to age. The distribution of Y. So now these are going to be, what are the predictions that we made? Well, we probably will see that those have changed as well, because while maybe overalls or some, I don't know, those little sparkly shoes that light up at the bottom, as much as I would like those shoes, those are more associated with kids. And that means that we'll see that data in our Y, which means our distribution of Y has changed. But what hasn't changed? Well, the relative distribution of X and Y has not changed. And maybe a little easier to grok, the expected values of Y for a given X is the same. So if I look at a single row of data and I see that they have all of these different information, the prediction that we make for a person that looked exactly the same as that probably hasn't changed. And so what does this represent? If you're familiar with this term, or other terms for drift, statistical terms for drift, this is covariate drift. So this is a change in the input distribution. And we can see this here. So if you look on the left here, what we see are inputs. So we have A here and B. And we see that our blue values here are kind of in a certain configuration, and they lead to B values here that are in a certain configuration. So those are two there, and then we see that those are blue, so this will be our labels here, A, and our labels here, B. And we see that even when we change the input distribution, so now we have our clumps a little closer together, this sort of kind of distribution of our colors, which is our Y, has not changed. So we see that largely blues are on this side of the line and greens are on this side of the line. So this is kind of representative of this change of the inputs, but this doesn't change so it does change the outputs, like the location of the outputs, but it doesn't change, for example, the relationship between the inputs and the outputs. Nor does it change the kind of relative distribution of inputs or outputs, right? So there's a certain number on this side, there's about an equal number on the other side. Okay, so that's one example. That's user behavior. So this is where this X has changed. And this is important to detect because this tells us about how customers are using our system. Really important, really helpful to understand how the business is going, this sort of thing. But this is very different from detecting, let's say, issues in our system. And so the next one is about system behavior and detecting changes in that. So let's start with the example again. So now let's say that some part of our company, maybe another team, has redefined item categories in our database. So while our model was using maybe item categories such as shirts, pants, so on and so forth, maybe they've changed this item categories to be much more specific. So now we no longer call them like bottoms or tops, maybe we've changed from shirts and pants and so on and so forth to something more general like bottoms and tops, that sort of thing. Well, if we've done that, this is actually a change in Y. So this is going to be a change in the output, but not the input necessarily. So we see X is the same overall, Y has changed. The relative distribution between X and Y has stayed the same. And then for a given X, so for a given customer description, the output that you give, the description of, what do I predict, has changed because it went from something like blouse to something like top. And so that's nominally changed, but even if it hasn't changed relative in distribution. So this can be best described as label drift. So we won't maybe go too far into this diagram here, but what you can see is that the X has stayed the same. So the positions of the dots for X1 and X2 has stayed exactly the same, but a couple less here, but our Y's has changed. So we can see here now our predictions here have changed. Okay, now let's go to our third one here, which is the underlying relationships. This is a much harder one. So let's start with our example. So our scenario is this: COVID has caused fundamental change in our shopping needs, right? So this is the beginning of 2020. It's such a great example because it's a clear example of kind of where the underlying relationship between concepts have changed. If you were, a retailer selling toilet paper, you had a certain sense of how much toilet paper you needed to sell every day. And then suddenly you went in and you saw that people were buying tons of toilet paper, right? And so this isn't a change in the number of customers we had or information about the sorts of customers that we've had. This is a change in the relationship between a customer and their toilet paper needs. Okay, we might have the same thing for clothes. So sticking with our example, you may have people who stopped buying, for example, clothes to go on vacation or sort of work clothing because they were all working, not everyone, but many people were working from home, and changed to buy more comfortable clothes. Maybe they didn't have enough of those. So what does this look like? Well, our distribution of X, the kind of customers that we're serving, that has stayed the same. But our distribution of Y, the sort of items, have changed. And not only that, but the relative distribution between X and Y has changed. And the expected values between X and Y, the most important part, has changed. And so this is what we call concept drift. So this is saying that there's a change in the distribution of Y given X. And we can see a picture right here. Okay, and then finally, I want to talk about data quality changes. So something that we're very, very concerned about often when we have a production system. And so I just wanted to give one example before we get there of, well, when we combine multiple scenarios, we might find that all of these things have changed, right? And now we need to start determining how can we determine which types of change we're having? How can we kind of disambiguate this? And we have a similar issue when we have data quality degradation. So let's say data was inaccurately collected or stored in our database. And affects both customer and like model information, so the outputs of our model. Then, all of these have changed. And that becomes a much harder problem now. Now we can't rely alone on the types of change relative to the distributions to determine what kind of issue was it. Was it user behavior? Was it a model change? Was it some sort of underlying trend change? Now we have to start thinking a little more clearly about our system and the possible changes that data quality could cause and deal with this sort of nebulous diagnosis problem. So, for example, there are 3 areas that data quality degrades most often within your system. So one is directly from the data source. Maybe when first collecting that data, we did poor measurement. Our script that measures how long a customer was sitting at the web page no longer works because we've changed something about the front end, something like this. Another is inside of the data systems or pipelines. So often for machine learning, before we pass it on to make a prediction, we're doing some sort of transformation of the data. That sort of data transformation or manipulation, maybe passing it in or out of a feature store, things like this could have changed. And then finally, when downstream systems consume them. So maybe our data was correct going into the model, but when and maybe coming out of the model, but when we've actually translated this into results, when we actually, publish the name of the item that we think the customer may use in our scenario, this is actually wrong somehow. So these are 3 kind of places that this can happen most often. And there are many, many different causes for this. So it could be delays or duplicate events in our system. Maybe we have a data set and we're accidentally tripling the number of customer clicks or something like this. Maybe we have a surge in outliers, right? We have some subset of customers that aren't really common in our data set for some reason came all today. And so this adds a number of outliers, which really affects the data quality. We talked about data distribution drifts quite a bit before. We might have missing events, right? So our system just wasn't capturing data for a couple of hours every day or something like this. We might have data type and format issues, that sort of stuff. There are 5 data characteristics that you can think about relating to quality. So things like the volume of your data. So again, just for context, this is kind of how do we think about data quality when we don't have this nice delineated difference between relative distributions? Well, we might need to look at characteristics like data volume, data freshness, data schema, data distribution, and data lineage. Okay, and I have about a minute left, so perfect for wrapping up here. So I just wanted to maybe give a brief overview of the different kind of parts that we've touched. So we have YLOCs, that's all about taking data and profiling it or compressing it so that we can use it as telemetry. But that relies on us having structured data. And Sometimes we don't have structured data, like in our example with text. And so what we want to do instead is create structured data. So how do we do that? We extract metrics, different signals from our text. And we use LangKit to do that, which is fully open source and able for you to download today. And then when you've extracted those signals, you want to pass them into some place where we can be actionable, where we can actually take those insights and use them right away, understand them over time. And we have that in our free YLabs Observatory product. And thank you. If you have any questions, I will stick around and answer them in chat right after I finish up this. But please do ask questions in chat, or feel free to join our community Slack, and I'll answer questions there. It was great talking to you, great thinking about drift and walking through a scenario. Thanks.